I am T.G. Manjunath, Associate Professor from Sai Vidya Institute of Technology, Bangalore. In the last few sessions, we have discussed time response analysis of first order system in the subject control system. In this video, let us discuss time response analysis of second order system. Let us consider a second order system. Our intention is to analyze the response. What is the meaning of response? Response is nothing but output. We want the response in time domain. Hence, we take the output as C of t. The corresponding frequency domain is represented as C of s. So, we are interested in finding C of t, that is response, time response. We are interested. So, for certain input, say R of t, reference in time domain, and its corresponding frequency domain is R of s. Now, a standard second order system is represented by the equation omega n square divided by s square plus 2 zeta omega n s plus omega n square. Here, this symbol is a Greek letter called as zeta, which is known as damping factor, or damping ratio. What is damping factor? Damping factor is nothing but the amount of damping present in the system. Damping will always try to resist the vibration. So damping will always try to resist the vibration of a system, or it is a kind of restriction against vibrations. Then what is omega n? Omega n is nothing but it is the natural frequency of oscillations. Natural frequency of oscillations. So measured in radians per second. So this damping factor is dimensionless, has no unit since it is ratio, but omega n is a natural frequency of oscillations measured in radians per second. This equation we call it as second order system equation because the maximum degree of s either in the numerator or in the denominator is 2. And this equation is also called as standard second order equation. It is called standard second order equation because of the two reasons. Here, the way the transfer function represented is with the two parameter zeta and omega n. Both are used consistently in most of the literatures. Hence, this is one of the reasons why it is called standard second order equation. The other reason being the way the transfer function here represented is not related to either the electrical system or a mechanical system or a hydraulic system. It is most generic. Hence, we call it as a standard second order equation. Here, the transfer function is given by omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now, in this closed loop transfer function, this denominator polynomial is called characteristic polynomial. That is s square plus 2 zeta omega n s plus omega n square is called characteristic polynomial. If this characteristic polynomial is equated to 0, s square plus 2 zeta omega n s plus omega n square, if it is equated to 0, then it is called characteristic equation. If I find the roots of this equation, roots of this equation, then those roots are called poles. So the roots of this characteristic equation are called poles, represented by cross mark. So pole is represented by this symbol. So always in general, the time response of any system depends upon poles of the system. What are the poles of the system? Poles are nothing but roots of this characteristic equation. Since the time response depends upon poles of this system, nothing but roots of this characteristic equation, let us find now the roots of this equation. Now the characteristic equation is given by s square plus 2 zeta omega n s plus omega n square is equal to 0. Now let us find the roots of this equation. So since this is a quadratic equation, I can find the roots very easily. So you know that it is in the form ax square plus bx plus c is equal to 0. And we know that x equal to minus b plus or minus root of b square minus 4ac divided by 2a. So in this equation, what is a? So a is equal to 1. What is b? 2 zeta omega n. C is equal to omega n square. Now x is what? Yes. Therefore, so two roots s1 and s2 is given by minus b, that is minus 2 zeta omega n plus or minus b square. So 2 zeta omega n whole square minus 4 ac. A is 1 and c is omega n square. So under root whole divided by 2a is 1. Now let us simplify this. Minus 2 zeta omega n plus or minus root of 4 zeta square omega n square minus 4 omega n square whole divided by 2. Now let us simplify further. s1 and s2 is equal to, if I divide by 2, we get minus zeta omega n plus or minus, if I take 2 inside the root, it becomes 4 and 4 get cancelled, we will get root of zeta square omega square minus omega square. So that is equal to minus zeta omega n plus or minus root of, if I take omega n outside, we will get zeta square minus 1. So here we got two roots of this characteristic equation, which is given by s1 and s2 is equal to minus zeta omega n plus or minus omega n into root of zeta square minus 1. Here for one root it is positive, the other root it is negative. Now let us analyze the nature of the roots. Let us analyze the value of the roots. You can see this equation. The two roots s1 and s2 completely depend upon the two parameters, that is zeta and omega n. But the nature of the roots is only depending upon zeta. What do you mean by nature of the root? Suppose if zeta is greater than 1, then inside the root the value is positive. When it is positive, we get the roots are real. Suppose if the zeta value is less than 1, inside the root it is negative or minus. So inside the root it is negative. So that it becomes j, means it is complex, imaginary. So here the nature of the roots s1 and s2 depends only on zeta, but the value of s1 and s2 depends upon both zeta and omega n. Now let us analyze what is the nature of the roots and how we can decide about the response of the second order system. So here, depending upon the value of zeta, we can have different cases. When zeta value is less than 1, in this we call the system is underdamped. Suppose if the value of zeta is equal to 1, then we call the system is critically damped. Critically damped. If the value of zeta here is greater than 1, we call the system as over-damped because the value of zeta is above 1. When the zeta value is equal to 0, we call the system as undamped. So, depending upon the value of zeta, we call the system as the following cases. So, zeta less than 1, underdamped, because zeta is under 1. Zeta is equal to 1, the system is called critically damped. Greater than 1, overdamped, is equal to 0, then the system is called as undamped. Now, we are going to take different cases depending upon the value of zeta, and we analyze the time response analysis of second order system for different test signals. That is, by applying different test signals as the input to the system, we are going to analyze its response, nothing but output, in the next videos. Thank you.